So now we move on to the next chapter, 7, Rotational Motion and the Law of Gravity. So we are going to switch gears now from linear, our understanding of the linear world, up, down, left, right, into space, to the rotational world. So we're going to look at defining angular speed and angular acceleration, rotational motion under constant angular acceleration, and then the relationships between angular and linear quantities. We're going to define centripetal acceleration and then look at Newtonian gravitation and Kepler's laws. So as we go through, we're going to investigate what circular motion looks like. So we're going to start looking at things that occur where we have a rotational motion. A specific type of two-dimensional motion then will be defined, and what we're going to build on here is understanding that as we move around a circle, we've got not only the length or the dimensions of the circle, but we've got things that are radial and diametric as well. So we're going to encounter new terms such as angular velocity, angular acceleration, centripetal acceleration, and we're going to show how we move then from this linear left-right, up-down world to the angular and rotational world. And we're going to see how this is very important when we try to understand the things that are happening, say, in our movement of the planet, movement of the other planets in the solar system, anything that has a rotational motion, understanding how we're able to put satellites into space. So to do this, we've got to understand some of the mechanics first. So the first mechanic that we need to look at and make sure we understand are the circular functions. So what we're going to do here is we're going to create something that I call the unit circle, and the unit in this case is the radius. Okay, the radius will equal 1. So if we strike this circle and we let the radius of that circle be 1, we can see that if we started at a point, the 3 o'clock position on the circle, or the exact horizontal, and we allow that, like the clocks of a hand, that radius to move through some angle, theta, that angle is something that we are going to measure now, not necessarily in degrees, although you will get some instances where this will happen, but we need to define the radian in this case, which we'll see is a unitless measure. And if we had, say, a pencil or a pen at the tip of that radius and it scored or struck a length, we would call that now S, or the arc length of a circle. Okay, so we're going to find out how that becomes important in understanding the number of times or the period of that radius spinning around the circle. Okay, and we're going to see how that applies to some vector relationships as well. So therefore, any angle theta measured in radians has to be defined by the angle. And in this case, we're going to define the angle theta as the arc length S divided by the radius. So as I said, since the radian is a pure number with no dimensions, we can see that this can then, by the definition, because theta is a ratio of an arc length to a radius, if we use that definition, theta defined as arc length over radius, if that arc length were, say, 1 meter, we just picked something arbitrary, 1 meter, and if we said that the radius was 2 meters, you can see the meters units disappear because they cancel out. And we're left with a number that's 0.5. And so we need to assign something to that 0.5 so that we follow our convention that I've been urging you to make sure you do throughout this course, is that you apply some kind of units to a number. Otherwise, it's just a meaningless number. So that number is going to now be called the rad, which is a half a radian in this case. So let's look at taking that definition of theta, the arc length over the radius, and let's move the terms around so that we now have an expression that defines or allows us to calculate for that arc length. So now we have the arc length S equal to the radian angle theta times the radius itself. Now, if we substitute one complete revolution, or the circumference, for that S, we now get theta equal to 2 pi. 360 degrees around the circle is 2 pi. So now we have a definition and an expression that allows us to calculate the length around that circle, the circumference, as 2 pi times the radius. So theta, defined as the arc length over the radius, is equal to, if we make the substitution of one complete circle, the circumference divided by the radius, is equal to 2 pi times the radius divided by the radius. The radius cancels out, and we have theta equal to 2 pi. So how can we look at the measure then of this circumference? We will see that the circumference around the circle is pi. Okay, well, how could we look at this? Well, if we were to set the circle up on a rigid pathway here and break it up into an increment that allowed us to measure that length, and hopefully you're seeing here what we're getting to is that value of 3.14, numbers going on to infinity. So let's take a simple example. Let's say we put some paint or a piece of tape on the edge of this rim, and we're going to start this rim rolling across that bottom line. And so when we do, we're going to either lay down the tape or lay down the paint, and we're going to measure from increment to increment what the length is that comes off of the edge of that rim. So out to point 1, out to point 2, out to point 3, you can see that we've got just a little bit left. So now when we finally roll it off so that the blue diamond then matches and lays down on the vertical or on the horizontal, we can see now that that length is the measure of pi. Okay, so now we have a value of pi that is 3.14 and numbers out to infinity. So now what we need to do is look at some of the mathematical relationships. We can quickly get a crude estimate of what pi is by doing some divisions also of a circle inside of a square and a diamond inside of that. So the circle of radius 1 has a circumference of 2 pi. So that's the radius, that's the circle. This number lies between the perimeters of the inscribed square and the circumscribed square. So mathematically, 2 pi is greater than 4 times the square root of 2, which is you can see the length here. Here's the square root of 2. 4 times that would be 4, all the way around. So we now have 2 pi being greater than 4 times the square root of 2, or less than 8, since the outer length of each side of the square is 2. So if we try to make it even easier, let's have everything so that pi now is greater than 2 times the square root of 2, or less than 4. Okay, so we're making some approximations by setting some boundaries. So 1.4 squared is equal to 1.96, which is less than 2. So now we have the square root of 2 is greater than 1.4. And we can set up the boundaries then that 2 is greater than 2 times the square root of 2 is greater than 2.18. So 2.18 pi is greater than 2.18 but less than 4. So A well-known rational approximation to pi then is to say that pi is approximately equal to 22/7. And if you ask your calculator for the number, the answer is 3.142857, off to infinity, correct to 2 places. So the idea here is to try to give you a pictorial or an understanding with an illustration of also what pi looks like. So now what we need to do is look at how do we develop our radian measurements. So when we come back, we're going to take again a look at this unit circle, and we're going to divide it up into radians.